While exploring a castle, Exena the Exterminator is spotted by a dragon who chases her down a hallway. Exena runs into a room and attempts to swing the heavy door shut before the dragon gets her. The door is initially perpendicular to the wall, so it must be turned through 90 degrees to close. The door is 3 meters tall and 1.25 meters wide, and it weighs 750 newtons. You can ignore the friction at the hinges. If Exena applies a force of 220 newtons at the edge of the door and perpendicular to it, how much time does it take for her to close the door? Dun dun dun. Okay, time for the fifth part of the video. In the original problem, we are told force is constant at 220 newtons, and that is perpendicular to the door. This means that we can use kinematic equations. Remember, we can only use these kinematic equations when force, and therefore acceleration, is constant. Now let's take a look at what the problem gives us. We are given the change in angle as well as initial angular velocity. We are also looking for time. This means that we should be using this kinematic equation that we are writing below. Change in angle equals initial angular velocity times time plus 1/2 angular acceleration times time squared. Now that we have our equation, let's start filling in what we know. We are looking for time, so that is obviously unknown currently. We are also given initial angular velocity because the door starts at rest, meaning initial angular velocity is 0. We are told in the problem that the door needs to be closed 90 degrees, meaning change in theta is 90 degrees. We will be rewriting this in the problem as pi over 2 because that's how we use in the kinematic equations. We don't currently have angular acceleration, but that can be found when we look for torque later. Now all of our variables are accounted for, so let's look for acceleration. Acceleration can be found through torque. So now let's look at the equation for torque. Torque equals inertia times angular acceleration. It also equals force times radius times sine theta. Now let's solve for alpha, or angular acceleration. So we should put alpha on one side of the equation and all the other variables on the other side. You can see that this will make alpha equals force times radius times sine of theta, all over inertia. We are given the radius, which can be described as how far the force is from the axis of rotation. This is basically the width of the door, 1.25 meters, since we are told Exena was pushing at the very edge of the door. Theta is equal to 90 degrees. Sine of theta is basically 1, so this part goes away. Next, we have to find inertia. The moment of inertia equation for a rectangular board with an axis of rotation on one edge, which is the shape of our door, is 1/3 mr squared. Mass can be found because we were told the door weighs 750 newtons, which is mass times gravity. I like to use 10 for gravity, so this means mass will equal 75 grams. The r in this equation is the same as before, 1.25 meters. Now we can look at this equation and do some simplifying. As said before, the sine of 90 degrees becomes 1, so you can basically take that part out. R over r squared can be simplified to just f over 1/3 mr. If you solve this out, you should get 7.04 for the angular acceleration. Now that we have all of our variables except for time, we can plug these into the original kinematic equation and solve for time. Change in theta is equal to pi over 2. Then you can plug in initial angular velocity, which is 0, so that term basically goes away. Next, you have 1/2 angular acceleration, which we found, times t squared, our unknown. Now let's simplify the equation and write it so that t is on one side and all the other variables are on the other side. You can see that this, once you finish this, it'll be pretty easy to solve for t. You have all your variables, and yeah. You can watch the rest of the work on the screen. And once you finish solving for t, you should get t equals 0.67 seconds. Thank you for watching. Bye!
No, but she got it towards the door.
Kiki! Kiki, over here! Kiki! Kiki!